Okay, let's talk about buffers. A buffer solution resists a change in pH, and this can be helpful for a life form, for example, a human being, or for a chemical experiment. It's composed of two things. You've got a weak acid or a weak base, so let's pick a weak acid, for example, acetic acid, and its conjugate, which means if you have acetic acid, you would have its conjugate base, which would be the acetate anion. Were it to be a weak base, it would be, if it was ammonia, for example, you could have the ammonium cation. That would be the weak base and its conjugate acid. Far more often, for some reason, you see the weak acid. And a lot of times it's acetic acid. So, let's see, the conjugate base in this case would be acetate. It could be sodium acetate, it could be potassium acetate, but the important thing is that you have the acetate there. The conjugate means that it's lost its H+. That's the H+ in acetic acid. Why is this mixture special? Well, let's consider what happens when you throw it in water. Oh, and by the way, you can prepare these things a few ways, right? If you need to have both, probably the simplest way is to buy some sodium acetate, buy some acetic acid, mix them together, bada bing, you're done. But suppose you also had acetic acid and throw in a less than stoichiometric amount of sodium hydroxide. That's going to react completely, and it's going to give you a buffer solution. You could also do the opposite. You could buy some sodium acetate and react that with less than equivalent amount of hydrochloric acid. If you think about that, that would do the same thing. It would give you a buffer solution. And I mention it now because it does show up in a lot of problems that they have a problem that you could call a system that makes a buffer. Not a system that is a buffer, but it makes a buffer solution. So watch out for that. Okay, what's special about these mixtures? Consider the reaction with water. So you've got acetic acid, which in a really technical sense is not an acid until that H+ is liberated. After all, it doesn't liberate it much, and so when it's covalently bonded, that's technically not an acid. But you react it in water, and to a certain extent it forms an acid and the acetate anion. That's fine, so that's a weak acid. But you also have this acetate in solution, and as soon as you react that with water, a small amount of it will pick up the H+ present in water and generate a small amount of OH-. So what you end up with is an acid and a base that's in solution at the same time. So to that extent, you could think of it as a buffer solution for that reason. You could also simply think of it as an acid and a weak base that's present to begin with. That seems to be, going both ways, if you will. And let's take a third look at it. If it contains both a weak acid and a weak base, it should neutralize both acids and bases. If you add acid to that solution, the acetate anion will react with it to form a neutral acetic acid, right? It soaks up that H+, if you will. If we add base, that will react with the acetic acid, and it will generate acetate anion and water. And that's a weak base there, but it absorbed the strong base, so to a certain extent that has also soaked up that OH-, and so in either way you are resisting a change in pH. Therefore, buffer solutions do resist a change in pH. If you look this up in other textbooks, or for example in Wikipedia, you can also see a Le Chatelier's principle explanation of this. Suffice it to say that buffer solutions resist a change in pH. Let's take a minute to ask ourselves if we have created a buffer solution. Somebody gives you a solution that contains these two things. Tell me, is it a buffer solution? This is potassium hydrogen phosphate, sometimes known as KHP. Notice that has lost a H+ from phosphoric acid. But if it's going to work, we need that to be a weak acid. Is that a weak acid and its conjugate base? It is. So yeah, phosphoric acid and its conjugate base. Is this a buffer solution? This is perchloric acid with sodium perchlorate. So we have an acid and its conjugate base. But you should have memorized that perchloric acid is a strong acid, which dissociates completely. So end of story. No, perchloric acid is strong. Here we have an unusual system. This is known as pyridine. And this is pyridinium hydrochloride. You know what? Well, Pyridine is a weak base. A lot of these organic amines are weak bases. And this is its conjugate acid. Somebody added H plus to it. So yeah, you got a buffer system there. Here's a nice simple one. HCl and KCl. Well, HCl is a strong acid, so right away it is not a buffer system. And by the way, KCl is just a neutral ion, so KCl is a neutral salt, so that doesn't do anything either. And here we have HCl and sodium acetate. You would think at first, no, strong acid and conjugate base, that makes no sense. But hold on, sodium acetate, what happens when it reacts with HCl? It would make acetic acid. So if you have an excess of HCl, I would agree, not a buffer solution. But if less than an excess, less than even a stoichiometric amount of this, it will react to form some acetic acid, and you will still have some remaining sodium acetate, and the HCl is gone since it reacted. So that's a tricky one, and the answer is yes. If sodium acetate was yes, if you had excess sodium acetate, because it would react to make some acetic acid, and you still have the sodium acetate, and you don't have the HCl, I already said that. So yes, it's a buffer system. You could also do the opposite, where you have acetic acid, and to that you add less than an equivalent of a base, such as sodium hydroxide. That's an introduction to buffers.